Good afternoon, everyone, and welcome to our new sessions of this seminar. Today, we will be gladly hosting Professor Özgen Çakır Çolak, and unfortunately, with an emergency situation happened, and I'll be delivering the introductory talk, which is going to be the first time in my life, but I just don't want to steal the show, so I'll be briefly introducing our professor and let her continue for presentation. Firstly, she received her PhD, the doctoral degrees, from RPI, Rensselaer Polytechnic Institute, and kind of less known in Turkey, but quite famous when it comes to mechanical engineering in the United States, in the world. And after that, she joined Baltimore University for 6 months for her postdoc studies. Then he returned to Turkey and started her academic journey. Right now, today she will deliver our talk as a faculty member of Istanbul Technical University, which also recently happened, according to her statement. Without further ado, I want to introduce her and leave the microphone for her to speak.
Thank you very much for a nice introduction. Hi everybody, good afternoon. Today I will talk about the material model development for polymers and polymer matrix nanocomposites. The outline of my presentation will be as follows. I will first of all start with the definition of the material models. What is a material model? And what are the challenges with polymers and nanocomposites? Then I will talk about the role of the material modeling in design. And then specifically, I will talk about the viscoplasticity theory based on overstress. Then graphene and graphene epoxy nanocomposites, I will mention about them. And then the last section will be a model development for nanocomposites, and I will give some simulation results at the end. So what is a material model? Why do we need a material model? Basically, a material model mathematically represents the relation between stress and strain. So we know that all the components, all the machine elements or parts under the effect of different loads. And as a result of these loads, we observe the stresses and the deformation. And we would like to find out the relation between them. So when we say that material model, or we call it constitutive law as well, for instance, what is the well-known material model for the metals? Everybody knows, I am sure. Hooke's law. Hooke's law is the material model which works well for the metal, for elastic behavior. But when we come to the polymers or nanocomposites, the situation is getting complicated. So it is not, it is much more complex and it is quite challenging. So that's why today I will talk about these material models. If you are going to use the polymers in the structure, how you are going to design it and how you are going to use the material models, or which material models should be used, and what is the process of, in fact, the development of these models. So why do we need these material models? If we answer that question, basically we would like to predict the mechanical behaviors under different loading conditions. And in the design process, clearly we use the finite elements quite a bit. So in the finite element analysis, we obtain the stress or strain distribution. So to be able to get this stress or strain distribution, we need to select the proper material model and use it in this tool. So that's why, as part of the design process, we need them. So when we mention, so what is different from the metals? We know that the metallic materials behaves elastically, and elastic and plastic behavior is observed. But when we come to the polymeric material, behavior is viscoelastic. So what is viscoelastic? So you can understand from the name also that it is a little bit like solid and a little bit like the viscous. So it is like a combination of elastic and viscous behavior, and it is basically called viscoelastic. So when the behavior is viscoelastic, what we observe is that material behavior is rate dependent. The meaning of the rate dependency, on the left side you see a stress strain curve at two different strain rates. So strain rate means that how fast you are loading or unloading the structure. If the material is elastic, we get only one curve. Okay? However, if it is a viscoelastic behavior, you can observe these two stress strain behaviors, because loading rate affect the material behavior. So this is one of the main difference from metals. So rate dependent, the other name is rate dependent behavior. There are, of course, a couple of other observations about the polymers, about this behavior. One of the behavior is creep, and the other one is the relaxation. So these are the common behaviors that we observe in polymeric materials. And on the right side, you can see some stress drop in the stress strain curve. This is basically the relaxation that we observe. Or some creep behavior. In the creep, in Turkish we call it sürünme. At constant load, we observe deformation on the material. So the deformation is not constant. With time, it changes. So these two behaviors, and in addition to this rate dependency, gives us the idea about the viscoelastic behavior, and we need to define these viscoelastic behaviors. This is just another comparison of these two behaviors. On the left side, we have the elastic behavior, and on the right side, you can see the rate dependency, creep, relaxation, nonlinear unloading behavior. These are all common behaviors that we observe in the material. And so we need to define such a behavior. Such rate dependency needs to be defined. For that purpose, different material models are used. The well-known is the Maxwell and Kelvin model. So viscoelasticity basically starts with this definition of the introduction of these Maxwell and Kelvin models, and then combination of them has been used quite extensively. Today, I would like to talk a little bit what should a model consist of in the case of viscoelastic or viscoplastic. Especially during the design process, if you are using a new material and if you do not know how it behaves or which material model you will select in the design, you have to know exactly what's going on or how we can define this behavior. So what should be the essential components of the viscoelastic model? When we consider the elastic behavior, we just use the spring. Okay, spring behavior tells us the elastic behavior. There is nothing else. But in the viscoelastic case, we include the dash pot element as well, because it gives us the information about this viscous behavior. So that's why I listed what is the common. So you need a spring element for elastic behavior, dash pot for viscous behavior, relaxation and creep. These are the two main concepts in the viscoelasticity. I don't know whether if you ever use any FEM tools, if you use some viscoelastic models, you may come across with this concept like creep or relaxation, because they are time-dependent behavior. With time, how the material behaves, it tells us. Constitutive law. Constitutive law is basically gives us the relation between stress and strain. So of course we need it. Of course, considering these spring and dashpot elements, it can be just one or a couple of them can be together, like in this case. And there are some other properties as well. If you are interested in temperature dependency, you need to include the temperature effects, or for some frequency dependency, you have to include other effects. But as an example, Maxwell, Kelvin, generalized Maxwell, standard linear solids, these are the material models for the viscoelastic behavior. When we come to the viscoplastic behavior, in fact, the metals behave viscoplastically, some of the metals, not all of them. But so for the metallic materials, you can also use the viscoplastic materials, because some of the material like stainless steel behave elastic and viscoplastic. So in the case of viscoplastic, again, you need the similar things. Apart from what I mentioned about the viscoelasticity, you need a yield surface. So what is yield surface? So in the elastic, if you are dealing with elastic and plastic behavior or viscoelastic, viscoplastic behavior, you have to figure out at which point the yielding occurs. Okay, everybody knows, I guess, what is yielding, akma in Turkish we call it. So you have to specify at which point it is going to yield, and for that purpose we need a yield function. Von Mises, I'm sure you guys heard it. So von Mises yield criterion has been used extensively, and these plasticity models, they are present as well. Hardening laws, because material harden. You remember the material classes, after the yielding, you observe some hardening. And you have to specify this hardening as well. And the materials are under the effect of cyclic load, not just only loading. So in this case, you need to define this kinematic hardening as well. So these are basically what should be in a viscoplastic model. Of course, constitutive law or strain rate formulation is also important phenomenon in these models. I put some of the material models in ANSYS. I select some the elastic, plastic, hyperelastic, and viscoelastic models. There are quite a bit material model. So in the process of selecting the proper one is important. As an engineer, your role should be which model is proper for your application. Otherwise, the FEM results doesn't have any meaning. If you didn't select the proper material model, so the rest is just garbage. Maybe if, but I see generally people who deal with finite element analysis, if you are especially working on the metals, elasticity modulus, Poisson's ratio, okay, that solved the problem. But for different materials, for polymers, for elastomers, etc., this selection on deciding on them which one is better or which one is proper is quite important. Okay. I'm going to talk a little bit. So these are what should be in each model. Each viscoelastic and viscoplastic model should contain these components. I don't know if there are some PhD students in the audience. If you are going to deal with this material development process, just in a couple of minutes, I would like to talk about what should be these steps and how you can develop the material model. The role of the material models I already mentioned a little bit, but if I say again, in the structural analysis, this is the most important component because it gives us the relation between stress and strain. So how we are going to develop the material model. In fact, today especially I would like to focus on this one. What are the main steps from where we have to start? Starting point is always experimental work. So you have to perform experiments at different loading conditions. On the right side, you see some of the results of the experiments. Considering this experimental work, we develop the material models because macroscopically whatever we observe, of course I'm talking about this one for the macro model, or it is called phenomenological model, or continuum theories we call it. There are different scales. There are so many different material models. In the second part, you can see the different scales. It goes from continuum to the micro, meso, nano. So there are so many scales. But as an engineers, we are interested in the macroscopic level models. But of course, the other material models are quite important because whatever we observe macroscopically depends on what's going on in the micro level. So that's why we have to know what is going on in the micro level and the connection. In fact, there are so many work is going on in this area. How we can link these models is another issue that we are dealing. After the development of the material models, so you have to implement it into the FEM tools and perform the structural analysis, optimize the structure that you do, whatever the design that you are doing. So this is the main steps that you have to perform. So specifically, after mentioning about these issues, I would like to talk about the VBO model that I've been developing over the years. This is the viscoplasticity theory. It has been developed by Erhard Krempel. He was such a nice guy. He was my PhD advisor while I was in RPI. He took the standard linear solid as a base. Standard linear solid is seen on the right side. Just it is like a spring and the dashpot elements. And from this SLS, he defined the overstress model. Overstress is, I don't know whether anyone is dealing with plasticity rules, etc. Generally, we mentioned that you need a yield surface. In this theory, we do not have a yield surface. Instead, we have overstress concept. And there are some state variables as well. And these are the formulations. These are the flow rule for the VBO model. In fact, this D is similar to the epsilon. Epsilon strain is used in the small deformation. If you go to the large deformation, it becomes rate of deformation tensor. So that's why the formulation is written as D elastic plus D viscoplastic. Basically, it is like a sum of elastic and viscoplastic behavior, or viscoelastic viscoplastic behavior. And the first section is basically Hooke's law, but the second section tells us the information about the viscoplastic behavior. And on the right side, you can see this SLS model, but some modified version. Spring and dashpot becomes nonlinear. We mentioned that for the viscoplastic region, kinematic hardening, isotropic hardening, or combinations are important. So that's why the model needs, you need to define these quantities into the theory as well. So K here is kinematic stress. It is used in the for to model the Barshner effect. Isotropic stress is for cyclic loading. I don't go in details of them, but basically in the theories we need them. We have also equilibrium stress, which is quite different from the some plasticity theories in the literature. The last, another formulation, the important formulation is the viscoplastic strain rate. This viscoplastic strain rate, considering the Eyring equation is this one. In 1936, Eyring defined this formulation, and he considers that yielding is controlled by some energy activation mechanisms, and he defined this formulation considering the activation energy and free volume, etc. And considering this formulation, I implemented or modified this formulation and use it in the VBO model, considering this Eyring formulation. So we mentioned that the material is rate dependent, also temperature dependent. So it means that you have to define elasticity modulus according to, as a function of the rate and the temperature. So are you guys familiar with this graph on the right side? What can it be? I don't know whether you have seen it in material classes. This is dynamic mechanical analysis result, DMA it is called. If you are dealing with polymers, definitely you have to run this test to find out the transition, to find out the glass transition temperature and how the properties is changing. This is important. And considering this DMA, we modify the elasticity modulus as a function of rate and the temperature as well. But in earlier version, for instance, we just use just the 1E. But this is the last form of the model. These are some simulation results. This unloading behavior, on the left side you see loading and unloading. Nonlinear unloading behavior is not an easy behavior that can be captured. If you go to the literature, you will see that most of the people just deal with loading. But when we come to the unloading, if it is nonlinear, it is not easy to define it. But with this modification and with we are able to simulate this behavior. On the right side bottom, this is multiple creep, which is also captured. Relaxation, these are important in the components. For instance, in a press fit application, relaxation important. In a preloaded screw connection, it is important because if you load a structure, you expect that load stay constant. It shouldn't drop. Creep for structural stability, it is quite important. If the deformation is increasing with time, so you lose the structural stability, it means that you cannot use this machine element anymore. So that's why you have to know how the material behaves if you are dealing with the polymers. What is also interesting in polymers, behavior is not just one type of behavior. For instance, in the metals, linear elastic hardening, that's it. But depends upon the materials, polymers behave differently. For instance, here, this is one, what is this one? PPO. Behavior of the PPO is something like this one. Epoxy's behavior is something like this one. Some linear behavior, yielding, softening, and hardening. So these are different behaviors that we observe. And with this model, we are able to capture all these rate dependency and temperature dependency as well. This is the some for hypothetical material, makeup material, it means. I showed some cyclic loading. We are able to capture it as well. So far, I just discussed the material models, viscoelastic material models, and specifically VBO model for polymers. Now I would like to talk about the nanocomposites, because what my PhD students and myself did or have been done, we are modifying the present models, model for polymers, and by modifying these models, we are able to model nanocomposites as well. So question is how we will go from polymer model to the nanocomposite modeling. I will discuss about it, but before that, I would like to mention a little bit what is nanocomposite. Okay. So could you just read a little bit while something is happening to my throat? So what I am sure you guys know the composite. What is composite? Mixture of the materials. So it means that there are at least two components. One component is called matrix. The second component is filler or reinforcement. Because polymer, when we looked at all the polymers, their strength is not high. Even though they have so many good properties, their strength is not high, so for every application we cannot use it. What we need to do, we can make composite. So this composite can be just a composite, or it can be nanocomposite. So when we say that composite, it means that the filler is not in the nanoscale, in the macro level, okay? But nanocomposites consist of at least two components. One is matrix, the other one is reinforcement. At least one component should be in the nanoscale. So in my case, we are working on the graphene epoxy nanocomposites. And the matrix is epoxy, araldite. Especially we select this matrix because it has been used in the aeronautical applications. Reinforcement is graphene, okay? Have you guys ever heard the graphene? Okay, because it is such a fantastic, when I say the fantastic, I always remember the Trump because he says everything is fantastic. But this is the fantastic material. Graphene is basically, what is the definition of the graphene? It is a two-dimensional carbon nanofiller. It has, you know the carbon nanotube on the right side. It is like a roll-up, okay? It is carbon nanotube. And the graphene is like a unfolded, okay? It is like just one sheet. What is the main material in the graphene? What can it be? Carbon, graphite. So with different manufacturing techniques, these graphite layers are separated from each other, and you get one single layer. One single layer, that's amazing. So who found out, he discovered this material? These guys, Andrei Jaim, Konstantin Novoselov, in 2010. And they got the Nobel Physics Prize.
Immediately, right?
Yes. So since then, for 15 years, 15, yes, there are so many researches going on in this area. As an academician in the academia world or in industry recently, they also started to work on it. And it has been started to use as a nano filler, okay? So what is interesting about this material? Can you look at this stress strain curve? What is the ultimate stress? Can you see? It is around 130 gigapascal. What is the strength of the steel, the strongest steel? couple of gigapascal. So it is quite 100 times stronger than the steel. Maraging, I think, the strongest one. What is elasticity modulus? 1 terapascal. And steel is 200 gigapascal. 5 times more, has a higher elasticity modulus. So that's why I am telling that it is really a fantastic material. But there is something, this is also some comparison, not only the mechanical properties, but other properties, electrical properties, thermal properties are amazing. So that's why for different application it has been used. You can see some application areas, some multifunctional graphene epoxy, insulating packaging, aerospace applications, I don't know, some sensor applications, automotive industry. Wherever you would like to decrease the weight and increase the strength, you can use these materials. Of course, there is something that even if as in the nanoscale, this is nanomaterial, in the nanoscale, the strength is that high, but you can maybe consider that how the stress strain behavior is captured. Can I use tensile testing equipment for them, for this? What do you think? How they get a one single layer carbon or graphene and test it? That is also something, I think, not the instrument that we have in our labs, we can do it. The method is nano-indentation. Nano-indentation in an atomic force microscopy. That is also something recently in the world. People in the Makina groups, they are quite interested in this one. So we know the atomic force microscopy or scanning electron microscopy. Generally, we use them for scanning the material. But they use it for testing as well. Okay, that is also something important. So it is called in situ SEM, in situ TEM. So because it is just one layer, the thickness or the layer is just one single layer. So how we are going to test it? This is the method. It is also something quite interesting. I will skip them. So it is that strong, that powerful, has so many properties. So let's use it and get the same result for the nanocomposites. We wish. But of course, there are some issues. At the nanoscale, they have such a powerful material, but when we use it in the nanocomposites, we do not get that powerful properties. The reason is these two reasons. What they are? Let's look at it. There are two main issues in the manufacturing. Gökhan, how much do I have time? Okay, thank you. One thing, when you use those nanoparticles in the polymers, of course, there is going to be an interface. There should be a connection from graphene to the matrix. This connection, you cannot establish it very well, it doesn't matter how powerful the graphene, you get nothing. So this is one thing. The one issue is this one. This interface needs to be developed. The second issue, you have to disperse, yaymak. You have to disperse the graphene evenly, homogeneously on the matrix. So if you cannot disperse the graphene, they agglomerate. Agglomeration is topaklanma. So they agglomerate. So initially you start with graphene, but at the end you get maybe graphite. So no use of so many information about the graphene. So that's why this uniform distribution is also important. What is this one? So for that purpose, what we have done, we have done the functionalization. Functionalization means you add some groups on the graphene so that it links the matrix better, okay? So let's assume that this is the matrix, this is the graphene. This connection is not good, but if I can make some wiring like that, so it can connect. So functionalization is basically this one. And this is the process that we are following in our lab. I will not go in details. Some mixing with some surfactant, sonication, and filtering, etc. And at the end, we get functionalized graphene. If you guys are working on the nanoparticles or nano materials, definitely you have to do a good characterization. So I have done this and I get the functionalization, so this is not enough. You have to prove it. You have to do the FITR, Raman, XRD, etc. So many the characterization so that you will figure out that really you get the functional graphene. So following this functionalization, we manufacture the nanocomposites. This is the method that we are using. We basically mix the graphene, functional graphene, with the epoxy, and then stir, magnetic stirring, and use the 3-roll milling. I think this is the, at least for us, the last method that we are using, because before we have used different methods, we didn't get the good results. This 3-roll milling, this work has been done as part of one of my TÜBİTAK 1001 project, and we get this 3-roll milling. What it makes, what do you think? So this is, it has, in fact, the machine has these 3 rolls. Hat deleme gibi bir şey. That just the 3 rolls, you pour the material here, and then on the picture you see, on the right picture, it just flows and you collect it. So what is the advantage of 3-roll milling? What do you think? The rolls rotates at different directions, and the distance is 5 micron between the rolls. So there are not, the space is just in the micron level. What do you think? What kind of effect can it have? Shear. So it applies the shear to the material. Due to this shear, this agglomeration is eliminated. So agglomeration is topaklanma. So we have seen that in our last couple of, we've already published a couple of them. And this gives a better result compared to the sonication. There are some other steps that you have to follow. And some characterization. Rate dependent, temperature dependent behaviors, and also creep and relaxation. These are must. It is a must, olmazsa. We have to perform this test so that we can understand how it behaves. For instance, in the creep resistance is improved quite a bit. Okan, do you remember how much? 40, 60%? I cannot see in this figure, but the black one is epoxy, the others nanocomposites. So it means that deformation is decreasing in the, so this is what we expect or what we want. Sorry about my voice. So these are what we are doing as in the material manufacturing and characterization side. And also we do the modeling of this material. So when you go from polymer to the nano, if I would like to use the same material, the same model, what kind of changes should I do? Anyone? Just read. Murat, read it and tell us what should be done. So as a polymer, we have just one component. In the nano or composite, we have at least two. So I need an effective one. So I should get the properties of polymer, and I should get the properties of nanofiller, and combine it and get the effective one. So that's why, in fact, the main thing is defining the effective elasticity modulus for elastic region. Mori Tanaka, these guys define this homogenization technique, and a lot of math. He defines the relation between reinforcement and the matrix, and from this Mori Tanaka, we end up effective stiffness tensor, and from here we get effective elasticity modulus. Okay. Sorry about that. When I don't teach, generally for a couple of weeks the same thing happens, and after that it's okay. But so this is for the viscoplastic region. These are some results. You may consider that sometimes when I listen this kind of seminars, if I see the stress strain curve, I say that, what is that? Just a stress strain curve. But really, it is not that easy process. Especially the left side is just the epoxy, the other two for nanocomposites. It means that you just add the properties of the graphene, and you get the stress strain curve. A lot of work, a lot of math. And the other behaviors, relaxation, DMA, high strain rate modeling, I haven't mentioned about it, but for the crash test, for the what is Darbe types applications, we need this behavior, and we are able to capture it. These are some works that we have done. And if I conclude, model is important, especially in the design. If you do not select the proper model, your analysis doesn't have any meaning. So select the proper material model. To be able to select or decide on the proper material model, you have to do the experiments. Because according to experiments, you are going to decide on which one is proper. So that's why not just the modeling, not just use FEM, but experiments, maybe manufacturing, if you are in the material side, and then use it properly. Maybe the last thing I haven't mentioned, that especially this machine learning is everywhere. So people started to use the machine learning techniques to model this material behavior as well, with the material models, sometimes without. So we will see what is going to happen, but there is also a big trend on this one. Maybe some PhD students, if you are at the point that you are going to decide on the subject, this is something that you may think about it. Thank you very much, and sorry about my voice. I should remind that I am looking for PhD students to implement this code into the FEM tools. So if you are interested in, you are welcome. My office is in the 425 Okay, thank you very much. Sorry. If you have questions, I will be happy.
That was the thing I was going to say. If you have any questions, we have a floor for questions right now, maybe like a couple minutes. And thank you for like completing your talk so selflessly so that you finalize it. Do we have any questions?
Firstly, thank you so much for presentation. And I want to ask you, there are multiple definitions of elastic modulus for determining the strength of polymers.
Mm-hmm.
So I wonder that how do we decide which of these modulus should be used in which situations, or do we have to determine the effective modulus of elasticity?
Yeah, that's good. That's right. That is something difficult. One of the difficult things about the polymers. For metals, you have only one elasticity modulus. That's it. So linear behavior, you get the elasticity modulus. But for polymers, there are different definitions. One of them can be initial part of the stress-strain curve. This is used. Another one is second modulus, which means that you second is like a Kirish from the stress strain, if it is a nonlinear, I have to mention. So it depends on whether behavior is linear or nonlinear. If it is linear, that's fine. You can just use one elasticity modulus, but it is going to be depends on the rate. So that's why the formulation similar to what I discussed should be used. But two different, so you should give a range, not just a one name. The second modulus, as I said, it is like a Kirish geçirme. The third one is tangent modulus. From one, if it is a nonlinear, you just, tangent is basically TET, so you just apply a tangent line and get the slope of it. But generally not the effective one. We don't use the effective one, but depends upon the nonlinearity. We use these different formulations. But most of the times maybe the initial slope will be fine. Mm-hmm. Is there any students, PhD students among us? No PhD students? Okay. I don't know. Most of you guys are undergrad. Okay. Okay, thank you very much for coming.